Thank you. Thanks everyone for coming. I'm a postdoc at Tel Aviv University. This is joint work with my advisor, Michal Feldman, who is here, and with Yakov, Babichenko, and Holzman from Technion. And I want to thank the organizers for inviting us. I think this is a very good talk for this session because, as the name suggests, we're going to introduce a new fair share notion. So the talk will be more conceptual, and there's a lot of open problems in the end. I'd love to hear your thoughts about all of that. So I'll begin with a quick introduction to fair division. So this problem asks, how should a set of agents find a set of items among themselves in a fair manner? Now, if you're not familiar with this, it's more of like a normative problem. We're trying to study, so there are many applications for this, but the easiest sort of picture you can draw is the following. You have n agents, you have a collection of m items. Here I have some office supplies, and you want to divide the items amongst the agents such that every item is assigned and every agent gets some bundle. And for this talk, we're only going to look at indivisible allocations, so no fraction allocations, and deterministic allocations. So we're not going to consider random allocations. Before we can do anything with this, we need to figure out what does it mean for an allocation to be fair. Right? So for the broad collection of fair division problems, the goal is to come up with some definitions of fairness that mirror our real-world idea of what it means for an allocation to be fair. And then we can ask questions like, does that always exist, a fair allocation, and can we efficiently compute one? So over the last few decades, the fair division community has come up with these two broad approaches to define fairness. One of them is envy-based fairness. The other is share-based fairness. In the envy-based fairness, each agent compares its bundle with the bundles of the other agents. And in share-based fairness, each agent compares its bundle with some threshold, some fair share, and is happy if its value is at least that share. And so in this talk, we're going to focus on the second thing. So some preliminaries about fair division. Every agent I has a valuation function V sub I that assigns a value to every bundle of items. The only assumptions we make is that Vi of the empty set is 0 and V is monotone increasing, because we're going to look at goods for now. And you can make some other assumptions on the structure of the valuations. For example, with additive valuations, the value of a bundle is the sum of the singleton values. I'm going to use this running example in the next few slides where you have two agents, Alice and Bob. The three items, the desk, the chair, and the laptop, and they have the additive valuations given by the table. So I'll begin with a quick summary of what we know about the first type of fairness via comparison. The sort of canonical fairness notion is envy-freeness from the divisible items literature. But of course, when you have indivisible items, and it's very easy to see that an EF allocation may not exist. For example, if you have one very valuable item, like the laptop here, the agent that gets it is going to be envied by the other agent. So the community has defined a lot of relaxations that allow for some bounded amount of envy. The most famous of these is EF1, where an allocation of EF1, if you allow for some envy from I to j, but whenever there's envy, there's some item g in j's bundle, where if j hides this item, then I no longer envies j. And it's well known, in this example, you can see that there's an EF1 allocation. This is not an accident. It's well known that EF1 allocations exist for the broadest class that we're considering, all profiles with monotone valuations. And this result from about 20 years ago now has led to a lot of work, a major research program, in trying to combine EF1 with other desirable properties, like on the welfare, operator optimality, and so on. And also there are other fairness via comparison notions, like epistemic EFX, which exists also for monotone valuations. And famously, EFX, which is a strengthening of EF1, for which we don't know yet whether it exists for monotone valuations or not. For all we know, it might. So I'm going to contrast this with the picture for fairness via shares. So here, an allocation is fair if, like I said, every agent gets at least its share. And the main thing we want to study is feasibility. So a share tau is feasible for the class of valuations C if for every profile of valuations, every instance from that class, there is a fair allocation. And we're going to call tau universally feasible if it's feasible for all monotone valuations. So what are the well-known shares in the literature? The most famous from many decades ago is the proportional share, where the proportional share is just each agent's value for all the items divided by n. In our example, since there's a high-valued laptop, the agent that doesn't get the laptop again doesn't reach its proportional share. And it turns out that no fractional proportional share is feasible. So for example, very simply, if you have two agents and one positively valued item, the agent that doesn't get the item gets nothing, and therefore no fractional proportional share. So there's also famously the maximum share that was defined by Budish about 13 years ago, where the agent partitions the items into n bundles and then gets the lowest valued bundle. The value of the maximum value of the lowest valued bundle in the partition is the maximum share. What about the feasibility of the maximum share? The MMS is infeasible even for additive valuations. But this led to a lot of work on multiplicative approximations of the MMS. which turn out to be feasible for many valuation classes. Structured classes like additive, submodular, etc. But as soon as you go to monotone valuations, again, no constant fraction is feasible. And you can see this with a very simple example of 4 items and 2 agents. So this, of course, there have been other shares in the literature, like the any price share and the truncated proportional share, but they have the same property. No constant fraction is feasible for monotone valuation. So this raises the question by contrasting this with the picture for NV-based fairness, where in that case we have many fair notions that are feasible for monotone valuations, but here no known non-trivial share and no constant approximation of any such share is feasible. So the question we ask is there a reasonable notion of a share that is feasible for all monotone valuations? And we're going to introduce one. We call it the Quantile share, and it's also very natural, extremely easily motivated. And it's based on these 2 simple ideas. The first one is to use the uniform allocation as a benchmark for fairness, the uniform random allocation. And the second is to measure fairness on the quantile scale rather than the value scale. So what does this mean? Consider the random allocation, the standard random allocation that gives each item to every agent independently with probability 1 over n. So the equivalent is it selects one uniformly from the n to the n possible allocations. And let xi be the random bundle of agent I in this random allocation. This parameterized share, the Q quantile share, is the Q quantile of the random variable Vi of xi, agent I's value for this random item. In other words, agent I asks, what is the probability that its bundle is valued at least as much as xi? And an allocation is Q fair if this probability is at least Q for all the agents I. And the question we're going to study here is for what values of Q is the Q quantile share feasible? Observe that the random bundle, like we're not doing any randomization here. We're comparing a deterministic allocation against the deterministic value threshold, the fair share. The random bundle just allows us to set that deterministic share value. I'm going to present an alternate motivation of this, which may be easier for you to understand what's going on. So an allocator who doesn't know the valuations uses the following procedure. So every agent submits a veto list of allocations of size at most L, and here fairness is captured by the fact that L is the same for all the players. And then the allocator produces an allocation that is not in any of the veto lists. So for example, here we have Alice and Bob in the 3 items, and there are 8 allocations. So suppose Alice vetoes 3 allocations, Bob vetoes some 3 allocations. There are 2 allocations that survive, so the allocator can pick one of the surviving allocations. And the question we want to ask is how large can the list be as a fraction of the number of allocations, such that the allocator's task is always possible? Now, in the absence of any assumptions, the answer seems trivial. It's like 1 over n, because in the worst case, if the lists are 1 over n, then you have n agents, they can cover all the allocations and kill off everything. But that does not take monotonicity into account. So a list is monotone consistent if it's consistent with some underlying monotone valuation, which means if an agent vetoes an allocation which it gets a bundle Si, it must veto all the allocations where it gets some subset of Si. If you enforce this, the question becomes, how large can the veto list be with monotone consistent list reports? And this is equivalent to the question about the values of Q on the previous slide. So that's what we study here. We show that for Q more than 1 over E, the Q quantile share is infeasible. Our main result is for Q at most 1 over 2E, a constant factor of Q here. The Q quantile share is feasible for all profiles of monotone valuations, assuming this famous conjecture of Erdos is true, the rainbow Erdos matching conjecture. And then we study some structured valuation classes, and we show that for constant values of Q, the Q quantile share is feasible, namely for Q at most 0.14 over E for additive. And we discover that Q equal to 1 over E is the exact critical value for unit demand and matrix rank valuations. Okay, so let's look at some simple infeasibility results to give you some intuition. The first thing we already said this earlier, the 1 over n quantile is feasible, and this is easy to see. If every agent eliminates less than a 1 over n fraction of the allocations, some allocation is going to survive. So, of course, the 1 over n quantile is feasible. In the other direction, the infeasibility of the 1 over E quantile also comes from a simple example. So let M, the number of items, be 1 less than the number of agents, and suppose the items are positively valued. Since you have fewer items than agents in every allocation, some agent gets nothing. So what is the probability that xi, the random bundle of agent I, is also the empty set? It's simply the probability that all of the n minus 1 items were given to someone else, right? So 1 minus 1 over n to the n minus 1, which is approximately 1 over E. And so the Q quantile share is infeasible for any Q more than 1 minus 1 over n to the n minus 1. Because for this example, below that threshold, the Q quantile share is 0. These two things immediately already solve this problem for n equal to 2 agents. Q equal to 1/2 is the critical threshold because 1/n is 1/2 and 1 minus 1/n to the n minus 1 is also 1/2. But in order to get the answer for larger values of n, we're going to have to use this conjecture. So I'm going to explain what the conjecture is and then connect it to the problem. Radish's conjecture says, given a k uniform hypergraph, so a family of k element sets, the matching number is the size of the largest matching, or the largest collection of pairwise disjoint sets in F. In this picture, we have a 6 uniform hypergraph with a matching containing 3 sets. So Erdos asked, how large, in terms of the number of sets in the family, can a k uniform hypergraph be if it has no n matching? And the conjecture is that for every value of nkn, such that m is at least kn, and for every family F that does not have an n matching, so whose matching number is less than n, the size of the family is at most the maximum of these two expressions. So what are these expressions? These are the conjectured extremal hypergraphs that have no n matching for every value of nkn. The first one is just all k element sets that contain at least one element of the first n minus 1 elements. Because if you were to take this family, you take any n sets in this family, they're going to intersect somewhere in the first n minus 1 elements. The second one is all k element subsets of the first kn minus 1 element. Again, if you were to take an n matching, it has to have at least kn elements. So if you're taking all k element subsets of kn minus 1 elements, they intersect somewhere. There's been a lot of literature on the Erdos matching conjecture. It's true for small values of k and n, and also it's true for m sufficiently large relative to k and n, and there's a lot of recent work in this area. But unfortunately, it's still a conjecture for the region of mkn that we're going to use it in. So how do we connect the Erdos matching conjecture and quantile shares? The first thing we have to do is reduce the quantile shares problem to considering only monotone 0-1 valuations, where the value of every bundle is either 0 or 1. So observe that the Q quantile share is feasible for all monotone valuations if and only if it's feasible for monotone 0-1 valuations. The one implication is, of course, direct. So for the other side, consider the Q quantile of a given monotone valuation. So you just order all of the bundles according to the value and take the Q quantile and construct a monotone 0-1 valuation in the following way. You set all of the bundles to the left of the Q quantile to value 0 and all of the bundles to the right to value 1. So now, if you want to give everyone a Q fair allocation in the 0-1 valuation, you're giving them a 1 bundle. And so it's Q fair in the original valuation. So it suffices to consider monotone 0-1 valuations in order to find bounds on Q. Okay, so we will use the Erdos matching conjecture as stated to first obtain a bound for identical valuations. So how do we connect these problems? You may be able to see some similarities already. The vertices are the ground set. The item step are the ground set, sorry. The hypergraph edges are the 1 bundles in the identical valuation function. And an n matching is a partition into n 1 bundles that we can assign to all of the agents, right? So if we say there's no n matching, that's equivalent to saying there's no partition into 1 bundles. But there is a difference between the two things. So what is k in the quantile shares problem? It turns out that a careful choice of k equal to floor of m over n minus 1 connects the two problems. I'll give you a quick high-level proof sketch. The high-level idea is that the Erdos matching conjecture says if there's no n matching, then there's an upper bound on the number of 1 bundles. So this implies that there's many 0 bundles, and that the Q quantile is at 0 instead of 1. So it's without loss to assume that m is sufficiently large, m over n is an integer, and k is m over n minus 1. You can do this by adding dummy items of value 0. And then you can show, via the Erdos matching conjecture, that a fraction of at most 1 minus 1 over e of the k subsets are 1 bundles. And so a fraction of at least 1 over e of the k subsets are 0 bundles. And then by the Kruskal-Katona theorem, a fraction of at least 1 over e of the k prime subsets, of any k prime less than k, are also 0 bundles. Kruskal-Katona just bounds the size of the shadow of a family of sets. And because we're considering monotone 0-1 valuations, if you have a 0-valued set of k elements, then all of its subsets are also 0-valued. Putting those two things together, then the random allocation xi the size of xi is at most its expectation probability about 1/2, and conditioning on this, vi of xi is 0, so xi is a 0 bundle, with probably about 1 over e. So in total, the probability of getting a 0 bundle is about 1 over 2e. Okay, for non-identical valuations, the proof is basically exactly the same. We use a rainbow version of the Erdos matching conjecture, which is a stronger conjecture. And it gives us that for non-identical valuations, if that conjecture is true, the 1 over 2e quantile share is feasible. We also have some unconditional results for structured valuation classes. For additive valuations, like I said, we show that the 0.14 over E quantile is feasible. In fact, we show that any EF1 allocation is 0.14 over E pair. We reduce it to the following problem. What is the probability that sum of IID Bernoulli variables is below its expectation? And then we can just find the answer in the literature. So it's known that the best bound so far is about 0.14. So any improvement on this bound also implies an improvement in our proposition. And finally, for unit demand and matroid rank, we discover the exact critical value. So for unit demand valuations, again, any EF1 allocation is 1 over E fair. And for matroid rank valuations, it's known that a maximum fair allocation exists and can be computed in polynomial time. And so we show that the quantile of the maximum share is at least approximately 1 over E. So then with some remarks, first, how does this compare with MMS? So given identical valuations, if the Q quantile share is feasible, if and only if the quantile of the MMS is always at least Q, because when you have identical valuations, you can assign the MMS partition, and also a Q fair allocation witnesses the MMS partition. And finally, you may think that Q quantile shares are feasible for monotone valuations because maybe they're weaker than the alpha maximum share, but this isn't true. It turns out that they're incompatible with the alpha maximum share, and they just measure fairness in units that are more appropriate for monotone valuations. It's also known from previous work that supermodular valuations capture all of the hardness from this problem. So if the Q quantile share is feasible for supermodular, it's feasible for all monotone valuations, for the same value of Q. And finally, you can ask this question, you can ask about the quantile share for bads as well, but it's not very interesting. So if a single bad is allocated, this bad is 1 over n fair to the agent that receives it. That solves the entire problem. The threshold is at 1 over n for all valuation classes. This, of course, leaves us with a lot of open problems. The first thing is to prove the unconditional feasibility for monotone valuations without the dependence on the Erdős matching conjecture. One way to do this is, of course, prove the Erdős matching conjecture. It's a big thing on its own. Another way to do this, which the combinatorics community hasn't really looked at for what we know, is to try to prove that the EMC bound is correct up to some constant factor, which would imply a constant factor for our problem as well. Other things you could do is find better bounds for additive or for other classes like submodular or subadditive, or to extend the study of quantiles to random allocations, arbitrary entitlements. We tend to conjecture that for monotone valuations and all of its subclasses, that 1 minus 1 over n to the n minus 1, so 1 over E is in fact the correct critical threshold. And the very simple n minus 1 item example I told you before is the extremal example. We proved this for 2 classes that we've seen, matroid rank and unit demand, but we also proved this analytically for small values of n and m, and by solving an IP for some slightly larger small values of n and m. But we also show that the 1 over 2E bound is tight if every agent must get approximately the same number of items. So even if you prove the Erdős matching conjecture, all you're doing is showing that the 1 over 2E bound is tight. And to get to 1 over E, you need some new techniques that assign unbalanced bundles to the agents. Finally, our arguments for monotone valuations are not constructive, just have an existence result. So this leaves a lot of open questions about algorithms or hardness for these types of problems. And most importantly, this is also the start of another big research program to combine quantile shares with other properties on fairness and efficiency, or to extend the idea of measuring fairness via quantiles to other problems beyond item allocation. That's the end of my talk. Thank you.